much, it's unstable. You're not going to indefinitely see it be stable and chilling in nature forever, just like electrons do, you know, protons do, neutrons do. So like those quarks that make up the protons and neutrons basically are in a way, you know, stable. They're interacting with each other in those sort of bound states of forming the proton and the neutron, and we see them to kind of just like be and exist in nature normally, naturally. But a muon, if you made one, even if it was naturally made or artificially made, it's gonna decay after on average time of 2.2 microseconds. So it's not quite really considered, it's not really a very stable particle. So when a muon decays, it transforms into an electron or a positron, a muon neutrino, and an electron antineutrino. So it's going to make, you know, some kind of electron or positron thingy thing and a couple of neutrinos, electron or positron, depending on whichever way. The mean lifetime of muon is the average time it takes for a muon to decay, which is about 2.197 microseconds, so around 2.2 microseconds. Due to the effects of special relativity, the decay time of muons can appear longer when measured by an observer in a different frame of reference, particularly when the muon is moving at speeds close to the speed of light. So very interesting fact, because time is relative. So depending on your frame of reference, if the muon is moving very fast, then its decay time could appear to be longer. The decay of muons provides evidence for the principles of special relativity, specifically time dilation. So super interesting. Muons are produced in the upper atmosphere when cosmic rays collide with atmospheric molecules. So by the way, we've actually covered an example, a very famous example of a cosmogenic interaction which makes muons. Now, of course, muons will decay further into electron or positron and neutrinos, but you know, we do make them naturally. It's just they're not a very stable particle. The decay of muons follows an exponential distribution, meaning that the probability of a muon decaying at any given time is proportional to the number of muons that have not yet decayed. And there you go. That's a little bit of a quantum probability E type of thing for you, because muons are tiny, and so they follow tiny physics laws, which is probabilistic in nature. Okay, using all right, so here's what they found as far as the quarks. We've got charm, strange, bottom, and top. Some weird names, but there you go. And another even heavier cousin of the electron called a tau, as well as two other particles with properties similar to the neutrino called muon neutrino and tau neutrino. So we've got, among the leptons, we've got electron, muon, tau. Then we've got electron neutrino, muon neutrino, and tau neutrino. So three flavors of neutrinos, which we named electron, muon, and tau neutrinos. The quarks, I named them up, down, charm, strange, bottom, and top. And then we also have bosons. We'll see what he talks when he mentions those, but those are the other type of family of particles. These particles are produced through high energy collisions. So what he means is these extra particles that we just mentioned. These particles are produced through high energy collisions and exist only ephemerally. They're not constituents of anything we typically encounter, but even this is not quite the end of the story. There's even more. So if you thought that we're discovering quite a few particles and, you know, is this the end of the story? Then not really. Each of these particles has an antiparticle partner, a particle of identical mass but opposite in certain other respects, such as its electric charge, as well as its charges with respect to other forces discussed below. For instance, the antiparticle particle of an electron is called a positron. It has exactly the same mass as an electron, but its electric charge is +1, whereas the electric charge of the electron is -1. So it has the opposite charge as the electron, the positron. And we talked about how in nature we have, in a different life, we talked about how in nature we have more electrons than positrons because there's more natural processes making electrons than there are making positrons. And poor positrons have been annihilated at various stages of this universe, so that we have very few of them, and we have very many more of the electrons. Okay. When in contact, matter